Hello again, everybody. For this video, we're going to be talking about what derivatives tell us about the shape of a graph of a function. And this is sections 4.1 and 4.3. Now, first up, we want to talk about extrema, which is a collective term for maximum and minimum values. And these can come in two flavors. We have the absolute and the local or relative extrema. So we'll say f of x has an absolute maximum at x equals c on a domain D. And by domain D, I just mean, like, for example, a closed interval. If f of c is greater than or equal to f of x for every x in D, which basically says if you have some subset of a domain, like a closed interval, then f of x has a highest value on that interval. And similarly, we'll have an absolute minimum if f of c is less than or equal to f of x. We'll say that f of x has a relative or a local maximum at x equals c if f of c is bigger than f of x for all x in some open interval containing c, which is just a fancy way of saying it's bigger at x equals c than it is at all the points near x equals c. And similarly, we'll say we have a relative or local minimum if f of c is smaller than the other x values. So from these definitions, we have the following theorem. We have the extreme value theorem, which says if f of x is continuous on a closed interval, then f of x contains both an absolute maximum and an absolute minimum on that interval. And similarly related to this, we have a so-called Fermat's theorem, although it's kind of a misleader because he has a heck of a ton of theorems, which says that if f of x has a local maximum or minimum at x equals c, and f prime of c exists, then f prime of c must be equal to 0. So in other words, if you want to find a relative minimum or maximum, then you're going to find out where the derivative is equal to 0. But this might not necessarily get you all of them, because if we take, for example, the absolute value of x minus 1, we know from previous sections that it's not differentiable here at x equal to 1. We have a cusp. The derivative is -1 on the left and it's +1 on the right. So the derivative does not exist there. But I still have a minimum here on the interval from 0 to 2. F of x has an absolute minimum of 0. But we'll notice that this doesn't actually fail the theorem I just wrote, because I don't have the condition that f prime of c exists. The derivative at x equals 1 does not exist, and so that doesn't tell me anything about my derivative or my minimum there. So we'll have the following condition, which comes in a definition. So we'll define critical numbers. A critical number is an x value c such that f prime of c is equal to 0, or f prime of c does not exist. And we have the following modification of the Fermat's theorem. It says that if x equals c is a local extremum, that is, it's a maximum or a minimum, then x equals c must be a critical number. So if I'm looking for maxes and mins, I want to find critical numbers. Not every critical number will give me a maximum or a minimum, but every maximum or minimum I find will come from a critical number. So anytime I'm looking for the maximum or minimum of a function, I want to start off by finding my critical numbers. And my critical numbers are again just these, where f prime of the x is equal to 0 or f prime of x does not exist. So let's try playing with these a little bit with an actual graph. f of x equal to x cubed minus x squared minus x looks something like this. So what I want to do is I want to talk about the maximums and minimums and stuff of this function. So from the picture at least, I've got a local maximum right here, and I'm at the top of a hump here. Down here I've got a local minimum. I'm at the bottom, so we'll talk about these. I'll say f of x is increasing if f prime of x is positive, and decreasing if it's negative. And we should already be familiar with these terms, but let's look at our first maximum there that we had. I have a slope equal to 0 there, and before that my slope is positive, and afterwards my slope is negative. I go up, and then I go down. And we can generalize this to our purposes. I can say if f prime of c is equal to 0, then I'm going to have one of four cases. Either f prime of x is positive and then negative, in which case I'm increasing and then decreasing, which means I have a maximum. Likewise, if I'm negative and then positive, I'll be decreasing and then increasing, which means I'll have a minimum. But I could have the case where I get negative on both sides of my critical number, in which case my critical number was something of a lie. And similarly is true for positive on both sides. So why don't we try to find out where those are by using this test with the first derivative. My function is x cubed minus x squared minus x. And I want to find the maximums and minimums, or the maxima and minima. So I'll take the first derivative, and try to find the critical points. And these are when the derivative is equal to 0 or when the derivative doesn't exist. But this is a polynomial and it always exists, so I could say that f prime of x does not exist never. F prime of x always exists. And when I set it equal to 0, I'll have 0 equals 3x squared minus 2x minus 1. And I should try to factor that. So I'll have a 3x here, and I'll have a 1x here. I'll have a positive 1 and a negative 1. So I think if I put a negative 1 here and a positive here, we'll have a factored version. And if we check this, we'll have 3x squared minus 3x plus x for a negative 2x minus 1, which means I have x equals 1 or negative 1/3. So these are my two critical points, but it doesn't tell me whether they are maximums or minimums. So I'll check around my critical points on a number line to find out where my derivative is positive and negative. Or, in other words, where the function is increasing and where it is decreasing. So if I plug negative 1 and 0 and 2, for example, if I plug in negative 1, I'll have 3 times negative 1 squared minus 2 times negative 1 minus 1. And that is equal to 3 plus 2 minus 1, which is 4. That's positive. If I plug in 0, I get -1. That's negative. And if I plug in 2, I get 3 times 4 minus 2 times 2 minus 1, which is 12, minus 4 minus 1, which is 7, which is again positive, so I'm positive here. So at my first critical point, -1/3, I switched from positive to negative. That's a maximum. And at my second critical point, when x is equal to 1, I switch from negative to positive. So that's a minimum. So this tells me I have a local max at x equal to -1/3, and I have a local min at x equal to 1. I don't know whether they're absolute maximums or minimums or not, because I don't have a domain and I don't have a very good picture. But if I look at the picture I do have, certainly it's believable that at -1/3 I had a maximum, and at +1 I had a minimum. But this process might not be exactly the same for all the functions, because, for example, I could have a very strange function which looks like this. It's got a little piece broken off over there, and I'm looking at it from A to B. Then based on my picture here, I have a local maximum at the top of this hump here, but I also have a local minimum at this free-floating dot, because this free-floating dot is below the rest of the curve, and so if I look at all the points, x values near the dot, they're up above. And this function that I've drawn here actually has a strange absolute minimum, which is on an endpoint, but the absolute maximum is at the top of a hump. So if I'm looking for the absolute maximum of a function on an interval, then I should be careful to choose the endpoints. So we'll go back to the picture I had here. F of x equals x cubed minus x squared minus x, and I'll look for the absolute maximums and minimums on the interval from -1 to 3. And this process would be the same as we had done before. We'll look for the local maximums and minimums, because they might be one of the absolutes. And then we also have to check the endpoints. So 1, we'll use critical points to find local extrema. And then 2, we'll use the endpoints, or rather I should say evaluate the endpoints. And finally, we'll compare all of these and choose the most extreme values. So before, my critical numbers were -1/3 and 1, and we found those both to be local extrema. So at x equal to -1/3, we had a max, and at x equal to 1, we had a min. Now I should evaluate this function at the endpoints. I need to find f of -1/3, the endpoints, f of -1 and f of 3. So this is -1 cubed minus -1 squared minus 1, which is equal to -1 minus 1 minus 1. Hold on, that's not right. This is minus -1. So this is a plus 1 at the end here. That gives us a -1. And if I plug in f of 3, I get 3 cubed minus 3 squared minus 3, which is 27 minus 9 minus 3, which comes out to 15. I'll probably have an absolute max there. And 3, I should compare these with the function values at the critical numbers. So I also need to calculate f of negative 1/3 and f of 1, which I'm sure is just a lovely number. I end up with negative 1/27 minus 1/9 plus 1/3. And if I find a common denominator, this is equal to 9 minus 3 minus 1/27, which is equal to 5/27, which is positive. And if I plug in 1, I'll have 1 cubed minus 1 squared minus 1, which is equal to 1 minus 1 minus 1, which is negative 1. Again, this actually matches the endpoint. So comparing all of these, I ended up with negative 1 from x equal to negative 1 and 1, and I got 5/27 from x equal to negative 1/3, and I got 15 from x equal to 3. X equal to 3 gave us the biggest function value, and x equal to negative 1 and 1 gave us the smallest function value. So I actually have two absolute maximums for this, or minimums I should say. So I have absolute minimums of negative 1 at two places, x equal to 1 and x equal to negative 1, and I have an absolute maximum of 15 at x equal to 3. So I had absolute extrema at both endpoints, but one of them matched a relative or local minimum on the interior. The second derivative will also tell us information about the graph, and it tells us the direction of the concavity of the graph. So we'll say f of x is concave up, or in technical terms, smiley uppy, if the second derivative is positive. And the function is concave down, or again in technical terms, frowny downy, if the second derivative is negative. And similar to what we had with the first derivative test, this gives me a condition for maximums and minimums. If f prime of c is equal to 0 and it's concave up, or f prime, double prime of c is greater than 0, that means I have a minimum, because the function is curving upwards away from the critical point on both sides. And likewise, if f prime of c is equal to 0 and f double prime of c is negative, or it's concave down, then I'll have a maximum. And sure enough, going back to that problem, the function I had before, I had critical numbers, x equal to negative 1/3 and x equal to 1, critical numbers, and I could just check the second derivative at these spots. So f prime of x was equal to 3x squared minus 2x minus 1, so f double prime of x is equal to 6x minus 2. And if I check the second derivative at each of my original critical numbers, I'll be able to tell which of them is a max and which of them is a minimum. So f double prime of negative 1/3 is equal to 6 times negative 1/3 minus 2, which is equal to negative 2 minus 2, which is negative 4, which is less than 0, which is concave down, which means I had a maximum there. And f double prime of 1 would be equal to 6x minus 2, 6 times 1 minus 2, which is equal to 6 minus 2, which is 4, which is positive, which is concave up, which means I have a minimum. Sometimes one of these will be easier to evaluate than the other, so try practicing with both. And with the second derivative, similar to the first derivative where we are able to find maximums and minimums and critical numbers, we have points of inflection with the second derivative. So we say f of x has an inflection point at c comma f of c, that's my xy coordinate, if f double prime of c is equal to 0 and f of x changes concavity at x equals c. That means my second derivative at c is equal to 0, but it's negative on one side and positive on the other. Similar to how when we were looking for maximums and minimums, I was looking for when the first derivative was negative on one side and positive on the other. And so we actually have a similar statement as we did for the first derivative. If f of x has an inflection point at c and f double prime of c exists, then f double prime of c must be equal to 0. Which means when we're looking for points of inflection, we actually do exactly the same thing as when we're looking for local maxes and mins. So if we're looking for points of inflection, then we want second critical numbers, where f double prime of x is equal to 0, or f double prime of x does not exist. Now, based on the definition of a point of inflection, I also need the function value to exist to have a point of inflection. So for example, g of x equal to 1 over x is concave up for positive x values and is concave down for negative x values. So it switches concavity at x equals 0, but x equals 0 is not a valid number to plug in. So I can say inflection occurs at x equals 0, but there's no point of inflection because g of 0 does not exist. So we can find a point of inflection for our favorite function today. I just need to find the second derivative and set it equal to 0, and check the concavity on either side of it. So we'll set this equal to 0, and we'll get 6x is equal to 2, or x is equal to positive 1/3. I'll do my number line thing, 1/3, and I'll test at 0 and x equals 1. F double prime of 0 is equal to negative 2, which is less than 0, so it's concave down here. And f double prime of 1 is equal to 6 minus 2, which is 4, which is greater than 0, so it's concave up here. So f of 1/3 exists, and it switches from concave down to concave up there, so 1/3 comma f of 1/3, whatever that is going to be a point of inflection. Both of these sections combined are set up for section 4.5, which is a summary and strategy for sketching curves without the aid of a computer algebra system, but I won't test strictly on that section until the third test. I want to test these two topics on their own beforehand so that we can have any feedback if we need it from the second exam before the third when we do the graphing.